Thank you. I always like when I get clapped before I start, just in case, you know. And it's also good to see such a diversity of ages. And since this is an engineering school, I have to say this because there's a lot of concern, genders. I don't know how many genders, but at least two. The town I come from, unfortunately, once passed something known as the bathroom law. And if you don't know it, count yourself lucky. What I want to talk about, though, is not that. You know, one of the intriguing things is that we live in a world where almost everything around us is designed. Almost everything. You look around, if you face the other way, you do see the odd tree and grass. But everything else, and I notice a lot of us are wearing glasses and we're wearing clothes. Actually, all of us are wearing clothes. Shoes. And I don't know about you, but I have bad teeth, so I have teeth that have been designed. Everything around us is designed, except that little bit of nature. And actually, us are increasingly being designed too in other ways. But it's a really odd thing that I can tell you a lot more about what happens to this table when I lean on it in terms of deformations and stresses and thermal transmittance than I can tell you about how designing works. Yet designing drives all this, right? Designing drives all of this. So what I want to do is to talk to you a little bit about studying designing. Designing is, and I'm going to give it a slightly different definition, is the intentional act of changing the world. That's what designers do. They intentionally change the world. If you're not making any change, you're wasting your time. Now, most of the change is minimal, but some of it is not. And when we look around, you know, we think of, you know, let's take Google, only because everyone's heard of Google. You know, Google has changed the world, and it did so by designing things. I mean, it's designing software that embodies ideas. So what I want to do is to talk about designing. And I'm not going to talk about engineering or architecture or software design. I'm just going to talk about this notion of designing. Let's see where we end up. So I've got three words there that maybe you're not familiar with. You shouldn't be surprised, I made them up. Cognitometrics, physiometrics, and neurometrics. The metrics part means measurement, right? It doesn't mean the metric system. So I want to talk about cognition. I want to talk about physiology, because that's us. And I want to talk about neurology, which is what happens in that special place. So what is cognition, and what therefore is design cognition? Design cognitive science deals with what happens in your mind. Now, you can argue about where the mind is or even what the mind is, but we all have this notion that there's something happening inside our heads, and sometimes we can glimpse that. So cognition deals with what happens in the mind, and it's a mental activity. And we use these words because without being scientists, we've already recognized that there's something going on. I mean, philosophers were the people who used to think about this a lot. So design cognition is the mental processes of sort of design, knowing, and doing. And you can find out things about your mind without ever digging into your head. that's a really interesting idea, right? That I can tell you a lot about your mind without ever trying to get inside your head, which is really good, because when I get inside your head, which we've done, we don't get many volunteers for this, by the way. So when you cut people open, we only cut dead people open, by the way, what you discover is the brain. You don't discover the mind. What that means is a different kind of talk. But so I want to talk about what happens in the mind. And cognitiometrics is that I also want to measure it, because I want to use the ideas of science. What are the ideas of science? What science says is it starts off with a fundamental axiom. Anyone have any idea what the fundamental axiom of science is? Yes? You have to yell.
The scientific process itself.
But what drives that? I mean, what you say is not wrong, it's just not enough. Okay. He's a good guy, because all of you are just sitting here. Right. The fundamental axiom of science is that there are things to be known. Right? If we don't believe that, we don't bother to study anything. So what I want to do is to take a scientific view of this. Physiometrics is the measurement of physiology, and we want to relate that to design cognition, what happens in our mind when we're designing. And neurometrics, of course, is the measurement of the brain, and we want to relate that to what's happening to everything. Because in the end, we're actually a single organism, and this is an arbitrary division that we love doing because it makes life easy to separate things out. Okay, so what on earth could we do to study design cognition? And here's a nice little example that has the word design fixation attached to it. So what is design fixation? If I'm a designer and I look at a design for the task I'm working on, does that affect the designs I'm capable of producing? That's a good question, right? I can see people here who look like they're either graduate students, or you've got to be careful nowadays, maybe very, very bright young professors. But whichever you are, this is a really interesting question for a designer, because it turns out the way we practice design, the way we're taught design, involves often showing or looking at design. So here's an experiment. The experiment looks like this. I have written out some instructions for the design task, and the design task is to design a device to allow a person with incomplete mobility to get in and out of a bath without changing the bath. I mean, today there are baths you can open up and so on. I gave that instruction to one group. These are actually students, actually multiple groups. I gave exactly the same instructions to another group, and except I added one thing. I said, on the other side of the paper is a drawing or a sketch to give you an idea of the level of detail we want in your design. And this is what was on the other side, not with all the markings on it, just the sketching. The sketching had two things intentionally there. The first were things that you would expect to find in a design. including things that don't make sense, right? If you just think about it, if you're sitting on this chair and you're going to reach over and you want to rotate, the chair rotates, you've got a handle, this can't work. Plus, there's lots of things that have nothing to do with it, right? The shape of the handle. We've got tiles, we've got this intersection. We've got some bad things here, like if you look at this, you'll find the taps are behind you. So the question is, if I show you this, not by telling you to copy it, but by simply saying, hey, this is the sort of level of detail we want, what happens? So we took mechanical engineers and industrial designers, just for interest. How many people here would think of themselves as students of mechanical engineering or mechanical engineers? Anyone? You don't have to be shy. Okay, a good percentage. Anybody here an industrial designer? Oh, good. Okay, so I just want to go, here are the sorts of features of things that were good, right? The people we didn't show the sketch to, you'll notice, apart from it being fixed, none of them had these features except the seat, right? This was in every design, or sorry, in a third of the designs, and they didn't have any of these. The ones we showed it to, look what happened, right? So here's a nice experiment that says, look, if I'm designing and I show you a design, it has a really big effect. But something really interesting and totally unexpected to show that industrial designers are not mechanical engineers. The control group of industrial designers had all this stuff in it, but the people we showed the sketch to had none of it. And there's some really interesting reasons why, and you have to come to a different kind of talk to find out. But industrial designers are not mechanical engineers. So here's some more. There's a technique. So the first one we might call a black box experiment. Here's some input, the designer, some output. We change the input, we get a change in output, and this black box in the middle presumably did it. And now we can infer. Here, this is another technique called protocol analysis, which is best described as data from verbal utterances. We spend most of our lives, well, we used to, talking to each other. We spend less and less, but we use a different mechanism. And of course, we're constantly providing information, intentionally or unintentionally. And what this does is it asks you, or doesn't even ask you, it just listens to you designing. And out of that, we transcribe what people say, and then we use a method to code up into categories what it is they've been saying. These are semantic categories. And what we end up with is we start off with a video, we transcribe it, we code it, we end up with a sequence of codes across time, which starts to capture what has been said. And it applies to individuals. These are students working. These are professionals I've had to blur it a bit, in an industrial setting. These are professionals in another industrial setting. It's a very generic technique. And the sort of coding scheme, don't look at this to read it. This is what the foundation of a coding scheme might look like. There's some theoretical constructs, and you end up with, in this case, 6 codes. So let's see. Here's actually, this is a company, a software company that should. So here these guys designing, and these are these 6 codes we talked about, and we can track that to show you where they're putting their cognitive effort. Are they thinking about the problem? Are they thinking about the solution? Are they thinking about how something works? Are they thinking about how should it work? What do they expect from it? Are they thinking about, well, wait a minute, let's draw this up? Are they looking at the drawing? Where are they getting this from? And we can track this as it goes along. Remember, it doesn't matter what these codes are, but these are the codes I talked about. This is a study done at Chris Williams is at Virginia Tech, looking at mechanical engineering students who take different majors. So in the beginning, they're all the same. So we measure them when they're freshmen, then we measure them a couple of years later. One group does the mechanical engineering course, which is, let's say, a more design course. The other group does engineering mechanics, the heavy mathematical modeling. And what's happened to them in between? So what this is the change in their cognitive behavior as they tackle the same task a couple of years later. And what do we see? Where are the big changes? We can see big changes here, and we can measure this statistically. But so what's happened is, not surprisingly, this thing which is measuring the behavior of the design, the people in engineering mechanics put a lot more of their time in that, and the people doing engineering design put a lot less. But people doing engineering design have now suddenly put a lot more time into drawing, into describing what they're doing. Because engineering mechanics people describe things mathematically, and they actually put a lot less time into that. So it's not so much what the results are, but the fact we're now able to measure the change in behavior, and this is all in your mind. Here's one where we're looking at high school students versus university students. How are they the same when they're designing? Because high school students have had no design education, and these are mechanical engineering students who have. And what we see is that there's really poor color resolution in your projector. But statistically, these two are very different. That what design education gives you is not more capacity to come up with ideas. I'm, of course, generalizing here. We'll see other things later. But more ability to manipulate those ideas. And when we study novices and experts, we discover something quite unexpected. Novices produce more, and I'll put it in quotes, creative solutions than experts, but they don't know they've done that. Right? They can't distinguish between solutions that are potentially good and those that aren't. Experts are very good at that, but they tend to narrow down the range of what they produce. Anyway, here's, this is some work done in Sweden with a group there, product service system design. Instead of just thinking of what you're designing as a product, think of it also as a service, which increasingly is the way we see the world. And in fact, slowly the product is disappearing, even though it's there, which if you're, with all due respect to people who do only mechanical engineering and think of the world as machines made up of molecules, not made up of bits, you're going to be stuck because the world is moving to encompass something much bigger. But there's really interesting things you can find. You notice that contrary to what we're taught, designers very rarely leave a blank sheet of paper or a blank screen in front of them. They really like to put ideas down at the beginning even. And the more of a master designer you are, a master designer is someone that other designers look up to and its name is associated with things, they tend to work very differently to the way we're taught. The way we're taught says, scope the problem. Look at all the stakeholders. I mean, it's so obvious. That must be right. Put up possibility. Try and understand things. Put up possibilities. Assess them. Go back. But when you look at what people do, so problem here is looking at the problem, making it up, trying to understand it. That's the blue. Red is when people put ideas down. People put ideas down really early on. And often this is because people are carrying around ideas that they're going to use next time. So we can capture all that today. This is no longer mysterious stuff. Here's one about teaching different concept generation techniques. This is something we do all the time. We teach you to do this, that, and so on. What's the effect of that? So here we're teaching brainstorming, which I presume you know, morphological analysis, which if you don't know, you should complain to your professors. But it's another method. And TRIZ, which is a really different kind of method. TRIZ is the only design method that ever came out of the Soviet Union, right? And survived the Soviet Union. Is actually used in the US motor car industry, and for all I know in Canada as well. But here, what we're interested in to see, are there differences in design cognition when you use different methods? Because if there aren't, why bother to teach them, right? If they just all give you the same stuff, let's just find the one that, actually then we don't need to teach any actually. You can just use whatever you do. And fortunately for professors, there's big differences. And just to give you some idea, these are design sessions. This is based on a lot of people. We divide the design sessions into deciles, which means 1/10 if you are not in the metric system. Sorry. And here we're measuring the ratio of where put your effort. You put it into thinking about the problem or thinking about the solution. The higher this number is, the more effort you put on the problem. The lower, the more effort you're putting into the solution. And it turns out that the theory is right. People put more effort into the problem at the beginning than at the end. But something's happened to morphological analysis. But anyway, big differences in what these methods make you do cognitively. It turns out that the tools you use, which of course is exactly what we would expect, the tools you use change you. Right? The tools we use change us. Got to think about all the stuff we do in life then. We're going to come back to this. And this is one I really like. Industrial designers and mechanical engineers. Here's a well-known task. It's actually how to redesign a coffee maker to make its footprint smaller. That's the task. We have teams of industrial designers, teams of mechanical engineers, and mixed teams. And what we're measuring is where they put their effort. The higher the value here, the more they put their effort on the problem. And then we give them a task of a kind they've never seen. Right? This is a task that involves existing knowledge. It's a personal entertainment system for the year 2025. I mean, you have to make it up. And look at what happens. Mechanical engineers basically turn it into a problem they know. They're in the sense that they don't put much more effort into thinking about the problem at all. Industrial designers totally change their behavior. And the mixed teams, the mechanical engineers dominate, they hardly change. Now you've got to ask yourself, if this is true, because this is an experiment, something is going on here. Something serious is going on here. If this were widely true, and this is an experiment with undergraduates, so it may or may not be widely true, but if it's widely true, it says don't go to mechanical engineers if you want something really new, right? Go to others. Go to industrial designers. Is that the sort of person you want to be? Right? Here's a nice little result from studying. This is a group in industry. They have an interesting task, which is a little different to what you might expect. It's a design group. And what they've been tasked to do is the following. They've been told, we have these 5 patents. We want you, and we've used them in a large-scale activity for whatever it is they've been doing. We want you to design a consumer product that uses one or more of these, because we own the intellectual property. We don't care what it is. We haven't told you what it is, but it's got to use this so no one else can get into this area. Interesting kind of problem. Not presented as, we have to throw an egg 10 meters so it doesn't break, where you know everything. Here it just says, we want to make money off our patents. And this is a design team which consists of Alan, who's the leader, whose background is primarily business, but he thinks he's a designer. Todd and Tommy are mechanical engineers. I've forgotten which, these are not their real names, in case you ever come across a team like this. Jack is a mechatronics person. Sandra is human-computer interface. Rodney's an intern. And I've actually forgotten who Chad is. What his background is clearly important. Now, what is this telling us? Okay. The size of the circle is the amount of words they uttered across all these design sessions. And Alan has talked the most. But, and that's not unsurprising, you can do an analysis called turn-taking to see who follows whom. But that's not what this is. What this does is it takes what people said and breaks it down into ideas, actually using the same method we alluded to before. So now it's possible, not turn-taking, that I say something, and then I follow that with another idea, and I follow that with another idea. So now I've had 3 turns, not just one. And you probably don't know what the next word means. I'm going to ask, does anybody know what a Markov model is? Okay, sort of. I'm going to tell you for free. We don't charge. Actually, we do, but not to students. The way to think of a Markov model, Markov was a Russian mathematician, quite brilliant. A Markov model tells you in a multi-state system, that is where there's more than one thing, if I'm sitting here, what's the probability of me moving to any other state? Right? So maybe the states are these ideas. And if I'm sitting at this idea, what's the probability of me moving to any other idea? And now we're going to measure, having measured that, who owns that idea or who said that idea. So this is the Markov model of, say, Alan. What's the probability of him moving to his own idea? Next. If Alan's talking, what's the probability that the next thing that will be said as an idea will be Alan saying it? And the number's going to go from 0 to 1. And what I've done is I picked the highest number for each of them. And you notice for each of them, they're talking to themselves. Right? That's actually quite important to recognize. That a lot, when we look at teams, we assume that it's always about interaction. It is, but a lot of the interaction is with yourself. And when I talked to Alan's manager, he was not surprised by this at all. He said, well, Alan's a pretty dominating and domineering person. But then we saw some other things here, which we put in dotted lines. Alan and Todd talk to each other a lot. And Todd and Tommy talk to each other a lot. Right? So they form these two sub-teams. So we can get out of looking at people and listening to them this, which tells us a lot. We can do all sorts of things. We can now look at how people, while they're designing, decompose and recompose the solutions they're generating, or even just the ideas. And we can study that. Now here we're doing students who are in this color, and engineers, professional engineers with 10 years experience. What's the difference in their behavior? And should we try and move students to look more like professionals? I don't know. That's a question in fundamental philosophy of education. Or we can measure surprising ideas that are unexpected, and how they get distributed across a session. What kind of groupings give you different distributions of surprising ideas? And this is 4 design sessions, and this is using a form of pedagogy which you use here, I know you use here, which is the studio pedagogy, where you have a tutor and a student. The bottom half is the tutor, the top half is the student. The gray area is when they're in the problem space, talking about problems, and the lighter areas when they're talking about solutions. And this tells you, if I'm sitting here and I'm a student, what's the place with the highest probability that's going to happen, that I or the tutor will end up on? And the answer is, if I'm a student and I'm looking at B, it doesn't matter what it means. I mean, of course it matters, but for us it doesn't matter. What we see is this. I'm here, I'm going to get a response from the tutor. I'm talking about the problem, and he's going to respond by talking about the solution. And what we can see is that there's these quite big changes over time in how the interaction between the tutor and the student occurs, and how after a while it sort of, now of course this is the end session. The point about this is not what you see here, but the fact that there are things you can see. We can now dig much more deeply into the cognitive behavior of people, of designers. I don't know about people at all, only about designers. And you engineers, you know what entropy is, right? Yes? This is not that. You've come across thermodynamic entropy. This is information entropy. Have you come across, does that mean anything to people? Yes, okay. It's the same idea, sort of, but in information theory. And for us, as people doing research into this, entropy, information entropy, is a measure of the potential of the space of ideas you're working in. It's a measure of the potential of the space of ideas you're working. The parts you haven't covered. Zero entropy means there's nothing to cover. Or one, if you normalize it between 0 and 1, there's nothing left to say. What this is, I hope, if I can just, is two designers, and we're measuring their entropy. That is the, as I said, the potential that is generated from the ideas they're producing. And you notice, you know, it starts off and then it starts to go up and it goes up. This is a moving average. They're not designing this fast, by the way. We've sped it up, in case you're wondering. And so this is amazing stuff to find, or to be able to measure. It's all post hoc. This isn't real time. I wish it were, but we're nowhere near producing real time. Okay, so that's telling us about the mind, that ineffable thing in your head. Physiology is much easier, and we can measure everything about you. And increasingly, you know, I don't know, the Apple Watch 4 tells you about your heart rate, and not just your heart rate, but whether you have arrhythmia and all sorts of things. Here, this is looking at parametric designing, and whoa, don't do that. And where are you looking while you're doing parametric designing? So this is an eye tracker. The bigger the circle, the more time you spend there. One really interesting thing, almost no menu activity, right? So if I'm the software designer for this package, I'd begin to ask myself, you know, maybe I need multiple modes. I mean, this is a group in China, by the way, but it's exactly, we did a parallel group in North Carolina, and it's the same. Now I want to look inside the brain. And it turns out we can without, you know, these are called non-invasive techniques, which probably implies there are invasive techniques. I don't know about those, and I want to steer clear of them. They did try that. There's some, I don't know if you've ever heard of, it's today a metaphor called the Nuremberg funnel. Right? And it doesn't take much to imagine and this was a 16th or 17th century idea, when people had this notion that you could have knowledge. They had this idea that if you could grind up the knowledge, you could shove it into the brain. They're probably not wrong, but they're maybe 500 years too early. All right? So what this is EEG work, electroencephalography. And what that does, it's a little cap that sits on your head with little probes that just sit on your scalp, and it measures the electrical signals running around the surface of the brain. Now, the brain is a nice, rich system. I mean, rich not just in size, it's probably, there's arguments, but it's about 50 billion neurons and a few trillion connections between them, which is big, but you know, people are starting to build computers about that size. But somehow that doesn't turn them into brains. The brain is a biochemical electrical device. There's lots of biological activity, lots of electrical activity, lots of chemical activity, and it's very rich. At the Krasnow Institute, we have a project. You might have heard of synapses, which is how one neuron connects to the other, and it's got a gap called the synapse. And there's got to be some way to pass through that gap. And there's a biochemical process that generates an electrical charge. The person building the model for that, it's currently about 30,000 lines of code. It's huge, very complex, just for that. This is measuring surface activity in the brain, and we know sort of the phrenology of the brain. If you don't know what phrenology is, it's not a good thing. Phrenology is a 19th century idea that said, I can tell about you by looking at the shape of your face. Right? If your eyes are close together, criminal tendencies, right? Big forehead, smart. Actually, that may be true, I don't know. But you know what I mean. Brain research is up to there at the moment. You know, if there's activity here, okay, you're speaking. Activity here, you know, that's the vision center. There's 6 or 8 of those. Right across here, decision making, insight, and so on. So we have this connection, sort of connection between behavior and activity. And here's the same person. So what you see here is, this is actually what's happening on the surface of the brain, but divided into frequency bands. This is actually the wave, just the amplitudes we get across the frequencies. A little bit more, we've got more frequencies we're measuring. And this is just a 3D model of what's being seen at a much more gross level. So the top one, for some reason my mouse always looks funny. All right. The top one is what happens when this person is doing a highly constrained task, more like what we would call problem solving. And the same person doing a much less constrained task, more like design. And what's interesting to see is we evoke different parts of our brain. And this is one person, but actually we get the same behavior. There are sometimes flips between people who are left-handed, but not all left-handed people have their brains switched. Actually, not that many. So there's fundamental differences in the way in which we operate in our brain. That is the machinery that drives things. And until we really understand that, you know, we're sort of working in the dark. So we did a whole bunch of mechanical engineers, now these are all practitioners, and a whole bunch of industrial designers. Right? Same task. Actually, we gave them 5 tasks. It's called the block experiment. We gave them a pre-task, which says, just do this so we can get a baseline for what you look like. And then we gave them the first task, a task that was the same as the first, but with fewer constraints. The third one, same as the second, but with fewer constraints. And the fourth task had no constraints. Okay, so there's 4 tasks here. How did people's brains behave? And now we're talking about 20 people, not 1. So this is the average for 20 people. This is the device we use to show you how the world has changed. When we started doing this, the device we used cost about $25,000. And you needed a PhD to run it, right? And that's before you got the software, because this isn't something that just comes out. There's a huge amount of processing needed. This, however, is the 799 US. I don't know, what is that, 2,000 American tomorrow? 2,000 Canadian tomorrow? I don't know. $799. You still need skill. Now, here's the results. Left-hand side is, they're normalized so that you can compare them. Let's see what we have. The dark blue, the orange is what we normalize everything against, right? So we said, this is task 1. We're going to make that 1. The things around it map onto these channels, which are located over the skull, and we know exactly what their cognitive measurements are. That is, this is where we think, decision-making under uncertainty occurs primarily here. The brain does everything all the time. It's really hard to make that claim, but there's more activation here when you're struggling with uncertainty than there is here. But there's more activation here, I'm not pointing to real places, here when you're struggling just to balance. There's no uncertainty. So there's pretty good regionalization. Okay. The interesting thing to see here are the following. In each case, these different tasks, so the pre-task is just to have you get familiar with this stuff and so we can see what's going on. This is the first task. We normalize it. These are the locations and these are the amplitude values. And all those other 3 tasks are in relation to that first task. Big differences. But look at the differences between mechanical engineers and industrial designers. I don't know what that means. This is ongoing right now. You're probably the second people in the world to see these results. And maybe, I've forgotten if we even showed this last time, which is a month or so ago. It could mean one of 2 things. And if you're a mechanical engineer, you will take the first one. And if you're an industrial designer, you'll take the second one. The first possibility is mechanical engineers find this so much easier, they don't need to work so hard. That's some industrial designer ringing up to complain. Or if you're an industrial designer, mechanical engineers are fundamentally lazy and are much more interested in something else while they're doing this. I don't know, right? And both of those don't make sense, by the way. But they do tell us that there is this profound difference in brain activation between domains. That's an incredible thing to find out, right? Really, we're all human beings. We're all made up of the same material. Now, we know that there's a lot of self-selection when people go into different educational tracks. It's not like we're all the same, then you do medicine and I do engineering, and therefore we're different. You know, people who go into medicine tend to be bloodthirsty. Tend to be people who want to do this, and people who go into engineering, generally, not always, but people, you know, who tinker around and, you know, see the world differently, much more pragmatic. But in many ways, both if I'm an educator or I'm running a business, I, in the long term, would want to know what's the meaning of this. And then we're getting near the end. This is using a different technique, but basically the same idea. What we're doing is we're getting a bit deeper into the brain now. So now we're looking at neuronal clusters in the brain, primarily in the prefrontal cortex, which runs here. It's the last part of the brain to develop, and it's the part of the brain that's associated with, you know, decision making, and, you know, you need that to be a philosopher, sort of thing. And it's the higher brain. It's not to do with motor activity. It's not to do with direct sensing. It's to do with ideas and emotions. And if you remember, we had these three concept generation techniques that we got people to use while they were designing. And cognitively, we found big differences. And now we look at the neurophysiology of this. And what do we find? So what are we showing here? What we're showing is these are all the sensors. This is a matrix of the sensors. And this is the correlation of activations. Red means highly correlated. This bit activates when this bit activates. They're correlated. Blue is, and so these are probabilities. Blue is 0.5, that's just, let's say, no correlation and increased correlation. Brainstorming occurs primarily in the right prefrontal cortex, which is here. Morphological analysis, which is a sort of structured technique that forces you to break things down, occurs here. I mean, it occurs everywhere, but this is the dominant activity. And TRIZ makes more of the brain active. People who use TRIZ tell you that they come up with solutions they could never have come up with without it. So, again, this is new stuff. This has all come out in the last couple of months. And so this is the sort of thing we're talking about, that, you know, we're getting these neural networks, and these are not computer programs. This is what's in your head that we're slowly beginning to find out about. And we're finding out all these really interesting things, like here's brainstorming, and this is across, you know, 20 odd, these are master's degree engineering students. And this is just dividing design sessions into ventiles. Didn't know that word before. Trying to find out what, you know, we know about deciles and quartiles, but we want to divide it into more. Took us a while to find what's 1/20th, right? Then, of course, we remembered that Starbucks had done our research for us. You know, they have a venti, and they got it right. But the interesting thing here is that the brain activation decays over time, and when you match that to number of ideas generated, you get a very strong correlation. So now we're beginning to, because the reason for that being interesting is that we've now started a project on how to change that. How can we change your brain activation for you to be able to produce more ideas? So, where to from here? Well, if you're a researcher, what this has done is sort of opened up lots and lots of possibilities. It gives you the opportunity to understand the effect of some of your teaching, which is different to pedagogy, the way in which you teach. If you are running a design organization, it gives you down the road the possibility to understand much more. I haven't shown you the results about team behavior and what happens when you, for example, introduce a new person into a team. What does it do to the cognitive behavior of the team? So to get more understanding, and then of course it lays the foundation for people to think about tools. Tools are one of the profound inventions of humans, the concept of tools to leverage ourselves. And we're slowly have been shifting from tools that make us more powerful physically. You know, I couldn't fly from Charlotte to Toronto, but people invented a tool that allows me to do that. We now have mental tools. You know, Mathematica, MATLAB allow you to do things you couldn't conceivably do yourself. But maybe we have other kinds of tools potentially coming along as well. Tools that give us the opportunity, not so much for us to be better, but for us to produce results that give us a better life. And after all, that's really the goal of all this. And I should tell you, the people who support this are not necessarily nice people, but they're very nice to support it. And with that, I'm going to stop and see if there are any questions. I don't know if you have the rule that I have, which is if there's no questions from the audience to the speaker then asks questions of the audience. Yes?
So you started today talking about the idea that design is intentionally changing the world. What happens when design unintentionally changes the world? I don't know if you have any thoughts or reflections to your research.
That happens all the time. Sometimes we think the results are bad, and sometimes we think they're really good. Is there anybody here who does not use messages on their phone? Anybody? Now, does anybody know why the SMS system, the messaging system, was put there in the first place? It was put there in the 70s, by the way, when the phone was invented, the cell phone. I'm going to tell you why. Originally, and still, voice requires a lot more power to transmit. And they were very worried because originally they weren't cell towers around, but they thought they wouldn't have enough. So they wanted a low power form of communication so you wouldn't stop using the phone. So they came up with this short messaging system, the SMS system, to keep you connected to them when you couldn't do it by voice. Today, there's roughly I've forgotten the number, it doesn't matter if it's 100 or 1,000 or 1,000,000 times more messages sent a day than there are voice messages. That's called an emergent property. And we think that's really good, right? There's a lot of bad stuff as well. Yes. And that's why there's now a developing area which has taken over the name of another area, and it's called systematic design, which sounds like it should be the process, but because that's what systematic design used to mean, but now it's come to mean encompassing design. That, okay, you've been tasked with this, but you have to look at all as much as you can. Yes?
If we were interested in learning more about the TRIZ method that you were talking about and seem to have some of those best results, do you have a recommended sort of first resource to go to?
Yes,
learn
Google.
about it? Google. Okay.
No, Wikipedia is a good place to start and look at their references. There is the TRIZ, by the way, is the Russian acronym for invention machine. The whole thing was invented by one person, Georg Altschuler, and it's really, I mean, it's become a real tool now, and it's, you know, it's got a whole software base and a society associated with it. But Wikipedia will then point you to some books. Yeah. Yes.
What's the difference between expect and structural behavior?
Okay. If I won't take your phone in case something bad happens, but I'll take it anyway. It looks, because I was going to throw something around, and, you know, it's all right. If I'm designing this, why do I worry about, say, screen intensity? Before I have it, anything like that is an expectation, right? If I have no expectation, I don't put it in, and then I don't measure it. So I, as a designer, decide, although sometimes society tells me, because, you know, there are all sorts of codes of practice and so on. But I, as a designer, decide what are the things I'm going to measure on this, right? So I notice on both of these, I expect to measure weight. Right? On this one, I expect also to measure how hard I have to press these rocker switches. Why isn't that here? If I don't think about that, I'm not going to put it in. Or coming back to the earlier question, Apple spends a lot of time worrying about what happens to this after you throw it away. Right? You can send it back to Apple and they rescue quite a lot of it. I really don't know, but I would be amazed if Kensington, who produced this, gave any thought to what happens to it afterwards. One is what you want out of it, and that's paralleled by what you get out of it. You don't measure things you don't know you want to measure, right? And if you get it wrong, unfortunate for everybody. And sometimes you don't know you have to measure it. You know, I don't know if you've seen the projections of early 20th century. If the motor car hadn't been invented, something interesting would have happened as the population of London went up and New York. By 1920, it would be roughly this deep in horse manure by the time the number of horses increased. No one gave any thought to that. But so if you don't expect it, you don't measure it. And if it's something that you should have worried about, like motor car exhaust pollution, well, we all pay the price. But a really important thing, designers decide or are told what behaviors they should design for. And that shapes what you do, and what you do shapes that. So, for example, if I don't know, there was a topic, 10, 15 years ago of having at the bottom for corporate office buildings, the reception desk should be made out of concrete, because people were throwing bombs all over the place. Okay, the minute you decide to make a desk out of concrete, you have new behaviors you have to worry about, like surface roughness. So it's a two-way street. But this distinction, this idea that you must know what you're designing for is critical. Yes?
So we educate a lot of engineers at this university. How do we teach them to be more like industrial designers in their approach to design, and less like the mechanical engineers you described in your studies?
The question I would ask before that is that what you want?
Okay, good question.
Right? What is it you want? What kind of people are you producing? So, for example, I did some consulting for a community college that wanted to get into design. And they originally wanted to get into it, let me say, from the soft end. And said that because that's their background. They was coming from the art department, and they wanted to see if that's what suited them. But it turned out they had no real understanding of what they wanted out of their graduates. I mean, they had all the standard stuff, be able to articulate and read and absorb, but no fundamental philosophy. And so without that, nothing happens. Well, no, nothing happens. You aren't in control. Now, if you want your engineers to be more, I'll use the term loosely, creative, you have to do this intentionally. It doesn't happen. Engineering in the 19th century, was a sort of skill. Before it got into universities, in Germany, which is where it sort of started in the mid-19th century, design was a big topic. But as engineering got into English-speaking universities, which were much more snooty, do you have that word, snooty? It wasn't academic enough for them. And particularly medicine didn't want to have more professions come in. You've got to understand this stuff, so that you didn't want more professions to come in because that diluted them. They said, you're not academic enough. So they took what was then the burgeoning engineering science and made that the core, not design. And it's taken 150 years, I think, to bring design back as that's what engineers do. They actually design. All of this other stuff is in the service of that. Of course you've got to know about that. If you don't know about mechanics and thermodynamics and fluids, you can't deal with that, the mechanical part of the world. But knowing that doesn't turn you into a designer. Right? It's sort of like all these professors teaching all these subjects and then saying, okay, you put all that together. Because that's what we sort of did for a long time. But it turns out there's another way of doing it. And that is to start with design and make all these topics subservient to design. Not to do away with them, because you've got to know them, but they aren't the drivers. And designing is different to learning about, Fourier series. Fourier series, the answer's in the back of the book. Of course, what's not in the back of the book is how do you set up anything? How do you even decide you should use this? That's not in the book, which is the hard part, it turns out. So if you want them to look more like industrial designers, assuming that's it, you decide that, and then you go about changing two things, and people only often change one. And sometimes you only need to change one. But if you're going to change the first, you must always change pedagogy, the way you do things. As the separate one is the curriculum, which is what you're teaching. Now that sounds crazy. The way you do things surely isn't going to have a big effect. It actually has a bigger effect in general than what you teach. The reason is that you can learn the stuff that's in books yourself. It's very hard to do it, by the way. And that's why people still come to universities. Good for us. But the way you teach things, so there's a whole wave over the last, 20 years. I mean, I used to be at Sydney University for a long time, and we started up a new degree because we felt there was a space that wasn't being handled. And this was what happens behind the screen. It's a new world out there. Turns out it's a world that can be as big as you can imagine. And it's not being designed, it's being produced. Generally by, I don't know what, anyone here whose background is computer science? Okay, but I can say this. I'm a computer scientists' surface interest in humans is surprisingly low. Because when you get them to design things, what they say is, well, why don't we cut the human out? It'll be much easier for me. Well, yeah, but that's not what it's about. All of this stuff was done by computer scientists, horrible, and we're suffering today dramatically. So we came up with this notion that you should design that space. And we finally got a new undergraduate degree at this 150-year-old university, which hadn't had a new degree for years, called design computing, where it was about design, but the language was computation. Right? And this was 20 years ago. And we started off with this different idea of pedagogy, studio-based. You start with studios. What are studios? They're different to working in labs, and they're different to project-based learning. Project-based learning, you give people the same project or similar, and they all work on it, and it's sort of reasonably well defined. Studios, what you work on is open-ended, and you get this interaction between the tutor and the student, and between students and students. And if you look at the money that's been spent on education research, which is huge, by the way, much, much more than spent on engineering education in any sense, what you discover is that the learning does not just take place between a professor and a student, or between the student and the knowledge base, but between students. Learning is a social activity, as well as other kinds of activity. And how do you tap into that? So now we have things like flipped classrooms. Instead of the professor standing up and telling you, this is what a Fourier series is like, or this is how you invert a matrix, you get that before you come into the classroom. You listen to some guy, it's always a guy, not many women, which is a real mistake, I think, but that's a different story. We'll give you a 6-minute talk from the guy who wrote the textbook on how to invert a matrix, right? And then you go and talk about it. That's what a flipped classroom is like. So the factual stuff, the knowledge, you get exposed to before, and you explore it in classroom. So there's lots of new pedagogies around. What's interesting is, unlike engineering, where if you make a mistake, the physics of the world aren't changed by you, bad things can happen, or good things. In education, nobody knows what happens. You trial something, people graduate, no one follows them, and then you say it worked. Right? That's crazy. Right? So we have projects very hard to get funding for, to track people for 20 years. And what you discover is, how's our time? Okay. What you discover is something fascinating. If you ask people about their education as they graduate, you get very interesting results. about the value of their education. Quite mixed. A lot of them say, a lot of the subjects were a total waste of time. Okay. 5 years out, a lot of them, now you get a slightly different response. They say some subjects turned out to be really useful. And they don't say a lot of them were a waste of time. 15 years out, you get a totally different response. I'm not using anything I learned. Fair enough. But the other question is, what in the curriculum would you change now that you're 15 years out? You know what the answer is? Nothing. Because when you are learning, you think what you're learning is everything. And what you don't realize until you get much further on, that actually what you're learning at a more fundamental level is a set of attitudes and approaches about how you deal with the world, which are conditioned by the knowledge that you learn. Now, of course, I'm giving you the extreme answers. Of course, there's still lots of people using their stuff. But the people we think of as successful always go into management or go into money. The two, unfortunately, are not as well connected. But, if you want to make money, you can't just be an engineer. You have to do more. And that's another kind of approach, So, I don't know, there's a small college in Massachusetts called Olin College, which is tiny, takes in 75 students per year into its engineering program, 300 students. Right? Its graduating class, which is generally 75, nobody drops out, but sometimes only 74 or 73, averages 8 startups. That's 10% of the entire, okay, small numbers and you've got to be careful about it, but that's incredible. 8 startups out of 75 people. They must be doing something different, right? And they are. Right? And you should find out about it if that's interesting to you. Right? So, more questions, or are we near?
There's room for one more question.
Yes.
I hear about design, not only in engineering, but also in architecture, interior design, fashion, and stuff. And I was wondering, do you think there are some concepts of design that are universal? And is there anything we can learn from studying designers in those fields that we can bring over to engineering to come up with creative solutions here?
I'm a believer, and it's a belief, in an axiom of design. An axiom, is a self-evident truth that is so obvious it needn't be tested. It probably can't be tested in some sense. And that is, designing is a human activity rather like other fundamental human intellectual activities that is practiced in lots of disciplines, and the way it's practiced makes it look very different. But fundamentally, all of them are the same. So when we study, we study all sorts of people. Software designers, hardware designers, mechanical engineers, electrical engineers, and architects, industrial designers, curriculum designers we've got into recently. Their behavior is fundamentally the same. It's only the way they exhibit it is different. Now, so I think designing is not science, it's not art, it's not engineering, it's not humanities. Designing is designing. Separate. And we've succeeded at Sydney University starting this year, although I'm not there anymore, to make designing a campus-wide course. Anyone can take it as an individual course or as a minor. You can be doing law, you can take it. You can be doing, medicine, you can take it. So that's that underlying approach. Coming back, obviously the way architects practice, the way industrial designers practice, is different to the way engineers practice. It's probably partly due to the way they're educated, not partly, largely, but not completely. And generally the differences have to do with what value you place on different aspects of what's going on. In engineering, value is placed very highly on two things: overt knowledge. Now, I'm talking about the distinctive differences, and the ability to evaluate, to calculate out what it does. If you can't do that, engineers get worried. Architects place surprisingly little value on overt knowledge, the stuff you find in textbooks. They place a lot more value on experience, and much less value on testing, because they can't. Tell me, does this space make you feel good when you look at a drawing of it? God, that's really hard. Even though it's hard, it's really important, though. It's really important. And so what happens is that architects develop a different set of skills, but what they're doing is no different. And so you can learn about architectural pedagogy, which has 150 years of studio experience, which, by the way, if you go back into engineering, was like that too. The great engineers taught in the master-apprentice approach. What you get out of studying what architecture looks like is that there's more than can be calculated mathematically. And if you're an engineer, I've been a professor of architecture, professor of mechanical engineering, civil engineering. I've been a professor of computer science and cognitive science. Each of these disciplines are amazingly different. You go inside them and they have this world that discounts what's outside, particularly any profession. Architecture is a protected profession, right? By law. You cannot call yourself an architect. You can call yourself a computer architect, but you can't. The word architect is protected. Engineer is not protected. Right? Anyone can call themselves an engineer. In Europe, they've taken a slightly different word, this engineer. So it's spelt differently. That's a protected word. You have to be chartered. You have to be registered. But when you go inside them, they look really different. Step outside, amazing commonalities. Really. So I'm going to finish with this little story. I don't know if you've ever heard of the Media Lab at MIT, but it's a profoundly influential lab that started about 25 years ago, actually by an architect, Nicholas Negroponte, who said that the world was becoming digital, which, of course, today we understand. But, 25 years ago, that was a serious idea, that everything was moving towards this digital world. And they became hugely successful. They got funding like you would not believe, and also produced stuff which we're using today. They just produced all sorts of things. You discover that Steve Jobs went to the Media Lab and got some ideas from there. That sort of thing. And I happen to know, Nicholas was an architect. I was on his master's thesis committee, which had nothing to do with computers, by the way, at that time. And I remember once we were having breakfast when the Media Lab was hugely successful. I mean, the Media Lab is a $200 million a year institution. Has typically 300 to 400 people working there on really outrageous stuff. And I said, how do you get a place like this to sustain itself? Because money doesn't do it. There's plenty of places with huge amounts of money and they die. Right? And he says, well, what he does is this. He always looks for bright, driven people and divides them into two. He didn't explain how. He appoints these people to work on an idea. But he also takes people who are bright and driven and so on and say, look, I want you to work on something unrelated to anything you've worked on before. Now, and they're both very, I don't know about the individuals, but generically that's very successful. Now think about that. There's got to be something in common, and that's this notion that you're driven and that you're smart, whatever that means. And the same really sort of applies in design and in pedagogy and all of that. That there's some key things about humans, and the question is, how do you get the most out of what you're looking for? Because in the end, what we want is to have a good life, and as designers, we want to change the world so other people have a good life. It's as simple as that. Thanks so much, John.